So now, just to show you that we can do a lot of things when we have a parametric equation, here's a small mystery. So what happens exactly near that bottom point? What does that curve look like? The computer tells us, well, it looks like it has some sort of pointy thing. But is that something on the display? Or is it actually what happens? So what do you think happens near the bottom point? Remember, we had that picture. Let me show it once more. Where you have these corner-like things at the bottom. Well, actually, is it indeed a corner with some angle between the two directions? Does it make an angle? Or is it actually a smooth curve without any corner, but we don't see it because it's too small to be visible on the computer screen? Does it actually make a loop? Or does it actually come down and then back up without going to the left or to the right and without making an angle? So, yeah, I see majority votes for answers number 2 or 4. And, well, at this point, we can't quite tell. So let's try to figure it out from these formulas. I mean, really, the way to answer that for sure is to actually look at the formulas. Okay, so question that we are trying to answer now is what happens near the bottom point. Okay, so how do we answer that? Well, we should probably try to find simpler formulas for these things. Okay? So, well, to simplify, maybe let's divide everything by A. Let's rescale everything by A. If you want, let's say that we take the unit of length to be the radius of our wheel. So instead of measuring things in feet or meters, we'll just measure them in wheel radius. So take the length unit to be equal to the radius. So that means we'll have A equals 1. Then our formulas are slightly simpler. We get x of theta is theta minus sine theta, and y equals 1 minus cosine. Okay, so if we want to understand what these things look like, maybe we should try to take some approximation. Okay? So what about approximations? Well, probably you know that if I take the sine of a very small angle, it's close to the actual angle itself, if theta is very small. And you know that the cosine of an angle that's very small is close to 1. Well, that's pretty good. If we use that, well, we'll get theta minus theta, 1 minus 1. It looks like it's not precise enough. We just get 0 and 0. That's not telling us much about what happens. Okay, so we need actually better approximations than that. So hopefully you have seen in one variable calculus something called Taylor expansion. That's okay. I see that. Okay, so if you have not seen Taylor expansion, or if somehow it was so traumatic that you've blocked it out of your memory, let me just remind you that Taylor expansion is a way to get a better approximation than just looking at the function and its derivative. So And here's an example of where it actually comes in handy in real life. So Taylor approximation says that if t is small, then the value of a function f of t is approximately equal to, well, our first guess, of course, would be f of 0. That's the roughest approximation. If we want to be a bit more precise, we know that when we change by t, well, t times the derivative comes in. That's the linear approximation to how the function changes. Now, if we want to be even more precise, then there's another term, which is t squared over 2 times the second derivative. And if you want to be even more precise, you'll have t cubed over 6 times the third derivative at 0. Okay? And you can continue and so on, but we won't need more. So if you use this here, it tells you that sine of a small angle theta, well, yeah, it looks like theta, but if we want to be more precise, then we should add minus theta cubed over 6. And cosine of theta, well, it's not quite 1, it's close to 1 minus theta squared over 2. Okay, so these are slightly better approximations of sine and cosine for small angles. So now if we try to figure out, again, what happens to our x of theta, well, that will be theta minus theta cubed over 6. That's theta cubed over 6. And y, on the other hand, is going to be 1 minus that. That's about theta squared over 2. So now which one of them is bigger when theta is small? Yeah, y is much larger. Okay, if you take the cube of a very small number, it becomes very, very, very small. So in fact, we can look at that. So let me say, x in absolute value is much bigger. It's much smaller than y. And in fact, what we can do is we can look at the ratio between y and x that tells us the slope with which we approach the origin. So y over x is, well, let's take the ratio of these two. That gives us 3 divided by theta. That tends to infinity when theta approaches 0. So that means that the slope of our curve near the origin is actually infinite. And so the correct picture is really something like this. Okay. So the instantaneous motion, if you had to describe what happens very, very close to the origin, is that your point is actually not moving to the left or to the right along with the wheel. It's moving down and then up. And of course, at the same time, it is actually moving a little bit forward at the same time. But the dominant motion near the origin is really that it goes down and then up. So answer number 4, you have a vertical tangent. Okay. I think I'm at the end of time. So have a nice weekend. And I'll see you on Tuesday. So on Tuesday, I will have practice exams for next week's test.